Hey guys, so this is the second part of our review of some of the topics from AP1 to get us going. So we're going to be talking about conservation of energy because we're going to jump into something called fluids here pretty soon, and really fluids is a rehashing of conservation. So off we go. This is the stuff we should be able to remember. Some of it might be a little new. So, potential energy, and you know what this is, the ability to do work by virtue of position. So there you go. Usually this has to do with gravity fields, right? So if you take something and you pick it up off the ground, you're doing work. And by moving something through a distance in that field, you're doing work, and that work is turning into potential. And if you guys remember, this is the equation. You can either call this potential energy or you can call it work. It's all the same stuff. Energy and work are the same thing. So there you go. Is this work negative or positive? Well, technically, there's no such thing as negative or positive work, right? Work is a scalar. Now, why is this? Well, energy and work are the same thing. And energy is not something that has a direction. You have a certain amount of energy, but you don't talk about it being left or right or up or down. Right. So really what's going on here is negative and positive have to do with which way is the force going and which way is the displacement, right? So in this case, it's positive because your displacement is down and your force is down, so it's positive. There you go. Gravitational. For some reason, a lot of texts call it U, which I hate, but I just call it PE or work, but a lot of texts do, right? There you go. There's the answer. Hope you got it. Yeah. Potential energy has to do with gravity fields, right? For the most part, if you don't have that field, that gravity field, if you don't have, say, a planet like Earth, well, then potential energy is not really a thing, right? And so it's just not going to be something that would happen. So this is the thing. All right, we didn't talk about this much last year. Conservative forces. Conservative forces don't really do any work. Weight is conservative. So like doing push-ups. You push yourself up, and then you come back down, right? It means that there was actually zero work done. Let's say you have a satellite and it goes around the Earth. Watch, around the Earth. I'm bald, right? How much work did that thing do? Well, it's zero because it begins and ends at the same spot. It's like asking how much work did I do for over my entire day. Well, if I begin and end in bed, I haven't done any work. Springs. Dear Lord, springs are a pain in the rear. Another example of conservativeness. Is that a word? Being conservative. Yes, springs can oscillate up and down. And so going one way will be positive, going the other way will be negative. If you guys remember, there's this equation, K is equal to Fx, or F is K over X. Right? We talked about the fact that as a spring goes up, gravity's pulling it down, and as the spring goes down, or as the block goes down, the spring's pulling it up. So there's always forces that are working in an opposite direction. Don't worry about it. Don't worry about it. I know it's crazy. It's okay. We're going to be all right. Work by conservative forces is independent of the pathway, so it doesn't matter how you get there. It's kind of like here again. You begin and end every day in bed, right? So it doesn't really matter what you've done. You haven't done any work. This is the thing. All right, non-conservative forces. This is where there is no energy conservation. The pathway depends. The best example of a non-conservative force I can think of is something like friction. And the reason is because friction always acts against, or not against, but I should say friction acts against the intended motion, right? So if this block here is going to go down, friction goes up. If you pull the block up the ramp, the frictional force changes direction. It's now down. And so because of that, friction is something that is non-conservative. Friction is always something that's trying to steal, take energy from us. And so it's this perfect non-conservative force. See, there you go. Boom. We can talk about the potential energy of a compressed spring. Work equals 1/2 kx squared. I always called this EPE for elastic potential. But this is something that hopefully you guys remember from last year. You can compress springs. Really, you can stretch them out too. A lot of times in a lot of problems we were compressing springs, and so the potential energy is equal to the work done in compressing it. Displacement is x. This is that equation I was telling you about a couple slides ago when I was just rambling on. This F for springs, oftentimes it changes direction. So it's usually negative F equals kx. But so what? Energy is conserved in any closed system or in the absence of friction. At the top you have potential, and somewhere in the middle here you have a combination of the two. You have some potential, you have some kinetic. At the bottom it all gets turned into kinetic just before it hits the ground. And so this is a constant. This looks like a lot of verbiage, right? At the top you got potential. Anywhere in the middle you got some potential, some kinetic. At the bottom you've got kinetic, right? The energy is the same at any one point as long as it's not, it's a closed system and there's not friction. That's why they say neglect air friction there. Here's an example of a problem. Conservation problem. And of course you can pause this. I might stop the video here. I can't remember what I'm going to do. Mass cancels out, which is kind of creepy. So the mass doesn't matter. And we can calculate the velocity at any one spot by doing this. We know what g is here on Earth. Right? We're going to calculate for v. We're going to solve for v. Calculate for v. There you go. Second example. See if you can figure out how this works. Conservation problems were hard for a lot of folks last year because you have to create your own equation depending on what's going on, right? You have potential at the top, kinetic at the bottom, and you're creating your own equations. And so when you have this equation here, right, at the top you have potential, no kinetic. At the bottom you have no potential and all kinetic. So what you end up with is mgh equal to 1/2 mv squared. The m's cancel out, you solve for v. You get this funky looking thing here when you set this equal to that and solve for v. And that's what they've done here. The m's cancel out. There's an answer. The answer is boring. Who gives a crap? And they have it in feet per second, which I think is strange. We usually use meters per second. It's an old PowerPoint. I'm fiddling with it. Here again, I told you I hate you. I don't hate you. I don't like that they use U. I wish they used PE for potential. I like that more, potential energy. But U is what you'll see. It's what you'll see on the test. This is the thing. Conservation's great because it's just what's happening over here, what's happening later, right? Beginning and end. And so I've always found these problems to be great because I just say, well, what's happening at the beginning? What's happening at the end? Was there energy taken away from the system, added to the system? There's an example of a problem. Ooh. Is there potential? Yes. Is there a spring? Well, no. We're talking about water falling off of a cliff, of a waterfall. Right? Is there velocity? Yes. So that's at the beginning, at the top. At the bottom, what happens? Is there a height? No. Is there a spring? No. Is there velocity? Yes. And so this is how dams work. We actually use dams in order to generate electricity, and we just use that energy transformation process as the water goes from the top of the dam to the bottom. And this is the thing. So you can create this equation, and it looks nasty. Whoa, whoa, whoa. Right? This is what you had before. This is what you have after. You can create these wacky-looking equations. Right? So we had height. We had a height. So the water was at a height at the beginning. And it had speed. It had a speed. It's 30. So we had 1/2 mv squared. When it got down to the bottom, there was no more potential. It was all kinetic at that point. We create this equation before equals after. All the m's cancel. You get this funky looking thing, and then we can do some mathematics. Math. So there you go. Did you get it? If you didn't, you didn't. That's all right. Do you understand the process? The process is what is important here. This basic process is what we're going to use for fluids for the most part. So if you understand this whole idea of total energy at the top equals energy at the bottom, and you understand how these equations are set up, you'll be all right. Another example. Same type of deal. All right, I think this is the end, and these are some wrap-up stuff. Problem-solving strategies. Read the problem. Mr. Atman always taught me, first thing you do is you relax. I think I taught you all that. And then you read. You have to read the problem. And drawing a picture is always a good thing to do. We need to work on that. For energy conservation problems, it's a little tricky because you have to know where the beginning is, where the end is, or where is the origin. Is it going to be at the bottom? Is it going to be at the top? And it kind of depends on you and what you want. But I think this is a good way to approach these problems. And this is a good review of the energy topics that we talked about last year. There you go. Say the same thing over and over again. I'm tired of it. I'm done. I'm pooped. All right. Hope that makes sense. You can always watch it again, and we're going to hopefully have some practice problems and so on and so forth. Thanks, guys.